Hello everybody. So previously we've talked about the idea of directed graphs and an algorithm related to them, which is topological sorting, which is sorting the graph into a list or an array in a way that the directions all flow in one way, or if that makes sense. So today we're going to be talking about another algorithm relating to directed graphs, and that will be called cycle detection. So if we recall in the graph vocabulary, a cycle is basically a path which you can cycle around basically. So in the following directed graph, this needs a direction. So this is obviously a cycle because we can keep going to these nodes, or like if you go to node 4, you're basically stuck in this cycle. But yeah, a cycle is basically, a cycle. It's very intuitive. And the algorithm is basically exactly what it sounds like. Given a graph, it just detects whether or not there are cycles in it. And here we are detecting cycles in a directed graph. So we can literally just do a depth first search and then add more stuff alongside it. So one such algorithm is basically keeping track of the nodes that have been visited in like an array or something, and then we can remember. So let's see how that might look like. So we start on node 1, so we write 1 down, and then we go to node 2, 2, and then 3, 4, 5, 6. But then we go back to node 4. Now this means that there is a cycle in this graph, right? So since from node 4 we have to go to node 5, and since we have arrived at node 4 once again, we are indefinitely stuck in this cycle. And there could be multiple cycles in a graph, but this particular algorithm only detects for this one cycle. And there could be like more nodes extending from here, here. But yeah, it's still very simple. You can just do a depth first search, except with a directed graph. So some directions are forbidden. And so this algorithm, this keeping track of visited nodes, very intuitive. This takes ON memory, which is, I think it's called linear memory, but I'm not sure. Well, it basically means that it's going to take as much time as the size of the input, like it's directly proportional. So if we like give 6 nodes, then it'll take around like 6 nodes of time, since it has to visit each individual node to find to look for cycles. So yeah, but this algorithm, even though it uses ON time, which is pretty alright, it uses ON memory, which could be too much for this particular algorithm if it's doing like very large inputs. So there's another algorithm that uses O1 memory, which is called Floyd's algorithm. So here we have one pointer. So Floyd's algorithm actually uses 2 pointers, A and B. So basically, while A is here, then we have B, and they start off in the same node, except every time node A goes forward 1 node and node B goes forward 2 nodes. So we can see this. So we can see here A and B, right? And then A goes to here, and then B goes to here. And then after that, A goes to here, and B goes to here, and A comes to here, and B comes to 1, 2, comes back to here. Now it basically detects, so it basically continues until the pointers meet each other again, right? So like starting from here, the pointers just don't meet each other. Not here, because at this point node B has already come to here. But at node 4, they do meet each other again. So this algorithm also happens to be ON memory, or ON time, not ON memory, sorry. But it uses O1 memory, since we don't have to like keep track of anything, right? So yeah, this is a basic Floyd's algorithm, which is a path detection algorithm. Goodbye.